Good afternoon. Most people call me Bill, although my legal name is William. I specialized in forecasting, in building high-impact weather forecast models for operational forecasters for many years. And right now I'm associated with the Arctic Weather Prediction Center in Edmonton, and we've built blizzard forecast models for the Arctic, and so I'll be talking a bit on that and some of the observations from the METARs. Not sure, how do you?
Green button.
Green? Okay. This work was published in Weather and Forecasting last year. We also had a condensed non-refereed article for general audience in the Polar Prediction Matters in 2018. And a few forecasts from these models were shown in a paper by Joe et al. In BAMS in 2016. So this is a photograph of clear sky blizzard conditions at Cambridge Bay. And this is what it's like. And when you're on the ground and blowing snow, you can see this is, we call it clear sky. You can see the sun dimly visible over there. This is very dangerous weather. If you're out in this and you don't have a point of reference, you don't know where you are. Whether you're in a vehicle or walking around, it's going to be tough. And from the air, you can't see the ground. So this is the most serious in winter, the most serious high-impact weather forecast problem that we have to deal with in the Arctic. As an introduction, land and air travel in the Arctic is increasing rapidly, and there's search and rescue flights, there's field research trips, there's military exercises, local Inuit hunting trips, and so on. And so a large portion of blizzard condition occurrences in the Arctic are clear sky, that is blowing snow alone without precipitating snow, and short to medium range forecasts are required for the whole Arctic domain. The Meteorological Service of Canada defines a blizzard for a warning as wind 40 kilometers an hour or more and snow less than a quarter miles visibility. It's extending for 6 hours or more. Some of the challenges, and there are many, the challenges to forecasting, there's a vast domain, few forecasters, limited decision time. Sparse METAR observations, most are on the coast. There's virtually none, very few inland. So there's no inland climatology to guide forecasters. For instance, if you need an aviation forecast covering an area. And actually, Curtis and I are working on a 40-year climatology using bias-corrected ERA 5 data. So that's still work in progress right now. Satellite coverage is not continuous in space and time over the Canadian Arctic. And polar night, there's no visible satellite to go by, and it's hard to distinguish blowing snow from snow on the ground. So just to pinpoint where the blizzards are occurring is not that easy. Typical environment for blizzard conditions, low temperature, strong low-level inversion, strong low-level wind, little direction change in a deep layer, a source of snow on the ground or falling, a less stable, moist, mixed layer extending a small distance from the ground. That's due to snow sublimating as it's lifted, and that reduces the stability, and so it makes it easier to lift snow off the ground. This is a typical radiosonde in clear sky blizzard sounding. At the time, this is from Baker Lake. It was reporting 0 miles in blowing snow. But you see strong wind and deep layer near the ground, little direction change. That surface wind is a mist plot on the plot there. cold temperature, strong low-level immersion, moist adiabatic lapse rate near the ground, and you can see the top of the blowing snow layer there. So any model of a weather element, you need to know the climatology of what you're dealing with. So we took 4 years of METAR observations from October through May, and we looked at the hours of blowing snow that were reported, or of blizzard conditions reported in those METARs for the 4-year period, and we actually use this as one of the predictans that we will be forecasting. But some of what you can see, the boreal forest boundary there in green, and so blizzards are relatively infrequent. In fact, they're almost zero south of the tree line, but most blizzards occur in the tundra region to the east and north of the tree line. These are the percentages you see in the Kavalik region, which is, I should learn how to use a pointer. I guess. Oh, the Kavalik region is here. So these are the highest percentages in the METARs of blizzard conditions reported. And also we had one station, Dewar Lakes, in the center of Baffin Island. That's a high tundra. So this is probably representative of most of the high tundra areas in the Arctic. About 5% blizzard conditions in the METARs. And we were interested in separating blowing snow from blowing snow plus snow observations. So we looked at only manned stations. Many auto stations only report wind, so they don't have the visibility. And some of them they don't report much at all, even just the temperature. So these are from manned stations, but you can see in the Kavalik region, 75 to 90% of the occurrences of blizzard conditions are in clear sky conditions. Clear sky above the ground, that is, but it's obscured by blowing snow. Most of the areas, half to 2/3 of blizzard condition reports are clear sky, except in sheltered regions. Yeah. So at the National Labs, where I work in Edmonton, we're with the Arctic Weather Center. We run 3 products for forecasting blizzards, and hourly forecasts 1 to 48 hours, driven by the Canadian Center for CCMEP CAPS Arctic model, and that was replaced with dual models. The HRDPS extends about to the Arctic coast, and the Nord HRDPS is a 2.5 kilometer model that covers the archipelago. Hourly forecast 1 to 84 hours, driven by the regional model at 10 kilometer resolution, and 3 hourly forecasts driven by the global model out to 120. So the first we have this is a rule-based model, the blizzard potential we call it, and it's rules for increasing severity of weather from drifting snow all the way up to blizzard conditions. Those are based on expert rules from forecasters. That's meant as a medium range heads-up prediction for an area. It wasn't really meant for particular sites. Then the Bagley-Hanesack models, I wrote the code for that, and we transferred that to CMC, and they're now running that now in Montreal. But we found that we can improve on those with machine learning models. And so what we did, we have 2 products there, probability visibility less than half a mile and less than a quarter mile. Observed blizzard conditions were matched with 43 predictors that are post-processed from NWP actually from the RDPS NWP. And we built with random forest, which is a binary yes-no classification system to forecast whether it's blizzard conditions or not blizzard conditions. And this is the results from, this is the quarter-mile model. In the first step, we offer all the predictors to the random forest, and then in the second step, throw out those that are with 20% or less importance of the maximum important predictor. So in the first step, that's with all of the models, all of the predictors in there. And then this is with tossing out the less important predictors. And these are the important types of predictors for forecasting blizzards. So max wind speed, surface to, it's roughly the seven lowest layers levels in the model, but it's roughly 640 meter deep layer. Then the Bagley-Hannasack, we actually use the forecast from that as a predictor, and that's a sort of a proxy for the snowpack condition, which is very important in blizzard forecasts, meridional wind speed, and so on down here. And we verified these with independent data. So this would be for the nowcasts. What we did with two types of verification, built a relative operating characteristic and the critical success index, and ranked them. And the random forest models are outperforming the Bagley-Hannasack models, which are the orange ones. This is no skill on the rock diagram is along the diagonal. So the area under the curve gives you a measure of the skill. But a rock diagram doesn't tell you, okay, if I'm forecasting, what's my threshold where I'm going to get the best success? So that we use a critical success index. It's a basic index, also known as the threat score. And you can see that somewhere in this region, around the 0.4 to, in this zone here, the best probability threshold to forecast yes for blowing snow or for blizzard conditions is around, 0.4 for, it's around 0.4 for the random forest and about 0.3 for the Bagley-Hannasack. And going out forecast lead time, we also found the random forest models are out predicting or have greater skill than all the way out to 72 hours. So CCMAP is interested now in using these in the weather on grid forecast, and we'll be working with them on that this fall. And just an example, this is a case from also written up in the paper, and you can see a very strong low here near Cornwallis Island, and very strong winds in the low levels over the Kavalik region. So this is the rule-based model, and it's the green areas would be mainly drifting snow, but increasing severity. Here's your region of blizzard conditions expected. This is a 4.5-day forecast, 108-hour forecast ahead of time. So it's basically saying, heads up, guys, we're going to have blizzards in the Kavalik region. This is the Bagley-Hannasack. This is a 84-hour forecast, forecasting the same type of high probability of blizzard conditions in the Kavalik. And this is the random forest, quarter-mile visibility, a 48-hour forecast. Basically, they're telling the same story, so we're telescoping down in time here to the time of the actual blizzard. And this is the caps. This is a 3-kilometer CAPS forecast ballot at the same time, and you get more definition there. It's a 24-hour forecast. And I believe that's it. Oh, and these are some of the OBS that, and the ones I circled are verifying our forecast there, so that they verified pretty well. One of the problems, of course, in verifying these Arctic forecasts is there's very few OBS to go by, and often there's no OBS at all to go by. But anyway, this one worked out pretty well. And with that, I'm done.
Time for a very quick question for this one. We did sort of slightly overrun. Maybe we should move on.